Hello everyone, good afternoon. I hope you guys are having good time here at Ceph with a lot of people around who are interested in Ceph, using Ceph, and developing Ceph. So I and Daniel are going to talk about today about what Ceph object storage can deliver as a secure high performance object storage. And a little bit of introduction about both of us, what we do at IBM. I manage a couple of teams, and one of the team is that who benchmark the Ceph performance in different kind of protocol. It could be block, object, or file. And this investigation or evaluation which we did was in that team only. And yeah, so we will go ahead and we'll talk about a little bit about the internals of this investigation, like how we achieved it. So, come here, Daniel, go ahead.
Yes, hi, hello everyone. I'm Daniel. I'm working on the product management side of things for object storage. And I really a substitute here because all of this work was done by Jay, that is part of Vikhyat's team. So I'm just trying to fill in that he couldn't join us. So thank you also for his work. That is really nice. So hope you enjoy it.
Thank you, Daniel. Yeah, and Jay was not able to come here because of some reasons. So we are presenting here. So, okay, so let's go back why we are here. So, we know that for any enterprise company, security is a paramount thing, right? That's the important thing. Or any users who are using software-defined storage with object storage, they think about the security as a first requirement. But at what cost, right? So, and it comes the $1 million question, that can we have an enterprise solution that can deliver security in a petabyte scale? So, or in other words, that the challenge massive data with the security. So when it comes to Ceph, I think the answer is yes, because as RGW is, that it provides a massive scalable S3 compatible object storage. And in a couple of next slides, we're going to talk about like how we are managing it. So then we want to answer a couple of key questions, like in this presentation, like how the number one is that how you will harden your security requirement, like, and what kind of overhead it can add. So the first thing which comes into mind that what is the impact on the client when the TLS or SSS is enabled. The second thing is that does internal encryption, which is nothing but the messenger v2 in Ceph, is it going to bump up the CPU requirement? The third thing is that how much overhead encryption at rest, which is nothing but the SSES3, is going to introduce. So these are some of the things when it comes with the security, when you add security on top of any high performance solution, it comes with a penalty, right? So you have to think about these kind of overhead. So we are going to answer that during this benchmarking, what we saw, how much of the percentage degradation or benefit we saw during this investigation. The second decision is that architecture decision, like are you going to use replica or are you going to use EC? That's the first decision which you want to make, depending on your storage efficiency requirement. Then if you are decided that EC, then in EC also, what kind of a profile you want to use? Are going to use a 2+2, as in K and M value? You might have, some of you might have attended the Bill and Alex talk about fast EC. They talked about different EC profile. In the same lines, we have in current supported 2+2, 4+2, and 8+3, which one is better as compared to the replication and how they are helping in the secure environment. The third thing is that which comes to the mind is that, okay, finally everything is done. We know our architecture, we have decided. Then what we want to do from the connection point of view, like are we going to use the RGW SSL direct, or are we going to terminate at going to use the HA proxy based ingress service? And the third thing which we will answer in this presentation would be the scale. Everyone loves scale, and Ceph is famous for that. And I think we're going to talk about like how different T-shirt sizes or the number of SSDs are going to help to achieve this performance. So in this whole investigation, this is our hardware configuration which we used. These are nothing but our Dell nodes. We call them all flash X5D nodes for storage nodes, and then we also name them as all Ceph ready nodes. But and then the second type of the nodes are nothing but the client node or data loaders, which are R760s, 660s. The configuration is listed here. I don't want to go in detail, but in this whole instruction, we have used 3 t-shirt sizes. One is a 4-node t-shirt size, the second one is an 8-node t-shirt size, the third one is the 12-node t-shirt size. That's, and the total OSD count was 96, 192, and 288. And the data pool was configured with replica 3, EC2 plus 2, 4 plus 2, and 8 plus 3. And the co-located daemons were Mon, Manager, OSD, and RGW in some of them, not in all of them. Depending on the scalability of the hardware or the config, we kept them aligned. So you can see that in the configuration side, we have a couple of the configuration disabled. Generally, in production environment, we don't recommend it. But as it was a benchmarking performance evaluation, we have to keep the numbers aligned in every part of the run. And some of the in-house operations like scrubbing or auto balancing or the PG auto scale, these are dynamic bucket sharding. If it runs in one of the investigation, the same run in different test case will not produce a similar effect. So we have to keep them disabled in all the investigation. Some of the version config which we use was the Albencho we have used for the running the client workload. HashiCorp Vault was used for the key management. Monitoring, we used Prometheus. And on the encryption, we have used SSL as a transit, SSE S3 as in like encryption at rest at the RGW layer, and the encryption at the wire was the Messenger V2 internal protocol which we have for the messenger. On the networking side, we were having 100 gig networks in our X5D nodes. They were bonded dual, but what we saw that network infrastructure which was configured in this whole environment was not enough for this performance investigation. We did need more investigation. Like if we had a 400 gig switch, we could have delivered much better performance on the read side of things, because we saw that the network was saturating when our get workload was running. So in conclusion, if you see that the results were that our gets were very fine, but we were saturating on the network. So I think I'm going to hand over to Daniel. He's going to talk about more on the charts, like how the performance was there, what we did when the network was, what we are planning to do, how the secured RGW and baseline RGWs were performing, and the comparison in different configurations. Over to you, Daniel.
Thank you. Yeah, so thank you for setting up the context for that. I just wanted to mention that you will see in the slides that they have like maybe loads of text, maybe too much, but the idea is that if someone gets these slides, can read through the results and check very quickly the results that we saw. We are mostly going to cover the actual graphs where we can see the results of the throughput and the different things. I also want to mention that there's a QR code in this slide. It's also a clickable link if you download the presentation from the site. And there you have like very detailed results of all of the testing that we did. Here, we're just going to share an overview. But if you want to go into the details, you can always go to that site and you will get all of the information there from the testing. OK, so going into the results. The first test that we have here is like scaling. So we just wanted to prove a thing that is always mentioned, that with Ceph, if we increase the number of nodes, the number of OSDs, we are not only going to get more raw capacity in the cluster, but we're actually going to get more performance. No? So we just wanted to make sure that that was the case. So we decided to do some testing with 4 nodes, 8 nodes, and 12 nodes. So that was really what was changing. And then we did a testing with erasure coding, different object sizes. And you can see here in the next slide that we have, like in the horizontal axis, the number of nodes that was increasing. And on the vertical axis, like the aggregated throughput and latency. And what you can see for puts and gets is that as we increase the number of nodes, there is almost a linear scaling in the throughput. And you would also see like a reduction in the average latency of the workload. No? So it behaves as expected in that sense. Also in this graph, what we have is like the CPU and memory resource utilization. So this is actually average core usage per RGW. And the nice thing from this slide is that as we increased the number of nodes, again, in the horizontal axis, you can see that actually the resources required reduced. No? So when we went to 12 nodes, we were requiring less CPU, or let's say that the workload was really spread among all of our nodes, and that reduced the average core usage per RGW. So the next test that we did is also about large objects. So we wanted to test like 32, well, we did with testing with different objects, but what we have here is like with 32 megabytes onwards, going higher than that, 64 megabytes, 256, we were reaching the network limit, as Vikhyat said. So we were with large objects, especially for reads, we were really limited by the network. But in any case, you can see here that we were able to achieve 111 gigabytes per second across 12 nodes. For reads, that's quite impressive. It's like 9.25 gigabytes per second per node. And that could go higher. No? But as you see, we're really in the limit of the NIC, of the physical NIC that was on those nodes. So that was really the limiting factor for this test. You can see here in this graph, this is for large objects. Again, in the horizontal axis, we have the client concurrency. So we increased the amount of clients that were pushing data into the cluster for writes. And there, as you can see, we got to like 110 gigabytes per second, in the throughput there. This is with a ratio code in 2+2, but again, if you go into the results, into the full results, you can see it for 8+3, 4+2, etc. So with the large object, the bottleneck was clearly the network. Then we tested the small objects, because with Ceph, we are starting to see with small objects also like a lot of high performance, low latency object storage workloads coming in, and people requesting these kind of object storage use cases. So we also want to have a cluster that is performance. Whoops, I really almost fall down there. So we need a cluster that is performant with object storage that has a small object. So we did some testing around this. Here you have results for 64K, a little small. I will show you better here. And in the end, the conclusion is that with reads, when you were doing gets, we were able to achieve up to 400,000 IOPS with a latency that didn't go over 2 milliseconds. That is quite impressive and a really good result for the kind of workload that we are targeting. For puts, we were able to get close to 100,000 IOPS. This is 64K. And as you can see on the right graph, once we were close to the 100,000 IOPS, the latency skyrocketed. So we hit like the barrier of performance, of saturation. And then the latency went up to 9 milliseconds in the average latency for doing writes. Again, here, the main limiting factor was CPU resources. So when you're working with small objects, you really need to be sure that your RGWs have enough CPU cores to provide the maximum IOPS possible. Now, if you're trying to target this use case specifically. So you can see here in the yellow lines that at certain points, we were consuming 10 cores, and this is 10 physical cores per RGW. So it's actually quite a lot of resources that were being consumed there. But really, the reason that you can see on the graph in the right why we were consuming so much CPU is also because the RGWs have to handle loads of requests. So we can see there that each RGW was handling like 10,000 requests, and we have 48 RGWs. So it's a lot of things going on there, a lot of requests that is being served, a lot of connections to manage. So yeah, there's high CPU consumption for small objects. Then we also tested with erasure coding versus replica 3. We really didn't plan for this test, but just because we had the result there, we said, okay, let's take a look and see how replica 3 is performing. As you would expect, replica 3 outperforms erasure coding in all of the cases. There's maybe a little bit of a difference with large objects when you're doing put, that there was only like 1% difference, but we can see here, no, in this graph, where we have in the horizontal axis, we have object sizes, and then you can see in blue is replica 3. The higher, the better. And we can see how the replica 3 for the gets now was providing much higher.
And I think it's completely aligned with the fast read requirement, the fast EC. So that was the main purpose of coming with fast EC, that it will help in the reads, which we are seeing here that it is not. So.
Yes, yeah, no, as you said, here if we go into the puts, this is the writes, there's not so much of a difference, but with the reads, there's a huge difference. And that's why the fast EC that is coming in Tentacle is going to be it's going to make such a positive change. The idea with fast EC was to provide a better experience for file and block, but also we're getting improvements in object, especially for small random workloads.
Right.
And not only that, we are also removing the padding that is really important, so the efficiency that we're going to get from the same storage is going to be much higher. So the fast EC is like one of those features that you really like to see, because without changing your hardware, without doing anything, you see a huge improvement in performance and efficiency.
Yes.
Just out of the box. That's like the nice thing about software-defined storage, no? Okay, so moving forward, we also wanted to see if we did encryption in transit from the client to the RGW, what would be the performance penalty, how much throughput are we going to lose, etc. Because we each time see more and more that we want to have fully secure deployments, so we want to have encryption at rest, in transit, everywhere. So this is an important factor, no? And what we tested was, okay, let's do a baseline without encryption, then let's try with the RGW, so terminating the SSL at the RGW, and also doing the SSL termination at the HA proxy, at the load balancer layer. And what we saw is that if we do the termination at the RGW, the performance penalty is almost negligible, so it's really small, the performance hit that you get. And we will also see that the CPU increase is around 20%, 10%, so it's not a huge increase in the CPU performance. So it's something like a no-brainer that if you're running object storage and you need to terminate your SSL, use encryption in transit, is a very good option, no? Doing it at the RGW. What we did see with HA proxy, that is, you know that in Ceph we have the ingress service, that is the load balancer that is provided by default when you want to load balance between your RGWs. And what we did see there is that we didn't expect is like quite a hit in the performance when we were doing the termination at the ingress. So this is also something that is under investigation, no? So we have Mark Kogan that is doing testing to see what happened here during the testing, and if there's something that we can improve from the default configuration of HA proxy when we're doing the SSL termination at the HA proxy layer. Yeah, and here you can see the results. Again, in the horizontal axis, it's just the client concurrency increasing. And as you can see, blue and red is without any SSL, so that's the baseline. And you can see that the blue line, that is RGW SSL, is really close to the red one, no? So the performance is almost the same. And the latency also goes more or less hand in hand. It's just with the ingress service, the yellow line, where you can see that we have like a reduction in the amount of throughput, and also the latency is worse. So that's something that we need to investigate and work on. And with puts, again, you can see here, no, that is very similar. With RGW SSL termination, we are very, very close to the performance that you get without any encryption. Okay, and this is moving forward. This that we have here is encryption in transit, but for the internal part of the cluster. So let's say that I want to have encryption between my OSDs, the RGWs, the monitors, all of the internal traffic. I want to have it also encrypted. You would configure the Messenger v2 secure option. And again, with this test, it was like a very pleasant surprise, or not surprise, but a very pleasant result in the sense that the performance, again, the performance hit was almost negligible, so you wouldn't even see the difference. You can see in this graph that we have here for puts and gets that the lines are almost together, no? So you won't really see.
Yeah, this was quite impressive. We were thinking that we'll hit it, we'll see some performance degradation, but when we saw the result and started deploying the graph, we were pretty surprised that, oh my God, this is, we can provide. I think maybe with this data at some point we want to enable secure as in like default also if someone wants to go with that path, like two kind of offering, one baseline offering and one secured offering.
Yeah, with this kind of result, you could say, okay, why not? No, why are you not going to enable it? So it makes sense.
Yes.
And I just wanted to leave this one here that also shows the CPU increase. You can see there that is 4. So for gets, it will be 4.2% increase in the amount of CPU consumed. And with puts, it will be 11% more. So there is a small CPU tax to pay when you enable it. But at the throughput, at the performance level, it's almost, you wouldn't notice. Okay, and this is the last one, so we don't want to bore you too much. The last test that we did is, okay, we have tested encryption in transit for the client and also for the internal communication of the cluster. Let's also check encryption at rest, no? And we did some testing with the server-side encryption option that is available in RGW, where you can configure a key manager, and then you're able to do per bucket encryption. And this is where we had our worst result, let's say. So here's where we really saw a big hit in the performance. You can see there that for gets, for example, it's up to 45%. And you can see also in the next slides, this is throughput for large objects that, okay, you could say large objects. It doesn't seem more or less is similar, but once you go into small objects, you can see that the thing gets ugly, no? The thing gets ugly. You can see there that in blue, we have the results when the server-side encryption is enabled. The only good news of this is that we already more or less expected this, and it's being already worked on by the RGW engineering team, because it's just a thing of the amount of round trips that you need to do to the key manager. We are not caching that kind of thing, so this is work in progress. It's already being fixed, worked on, so we expect to have for next year better results if we do the testing again with the fast EC plus the work that is going to be done.
Maybe a 2.0 will be better.
Yeah, so we should see an improvement here. Yeah, so recommendations or takeaways from the testing that we did. Predictable scale, so you can add nodes. You can keep increasing your throughput as you add nodes. That's clear. Also, the throughput plus the IOPS was quite good news, especially that 2 milliseconds in the latency for the read workloads with a very, very high concurrency. Very good news for this kind of high-performance object, low-latency workloads. And then the best thing out of all, I think, is the minimal security overhead. No? So we did see that doing the, let's say, the encryption at the RGW, so you're terminating your SSL at the RGW, plus enabling Messenger v2, almost didn't have any impact in the performance. So this is great news. It's true that you need a little bit of extra CPU, but the performance didn't suffer. So that, I think that for me, that was like the best result out of all. I don't know if you have any other
No, we don't.
remarks.
Questions?
So if anyone has questions. Yeah, if you don't mind getting over to the mic, Jiffin.
So regarding the encryption at rest, do you have any comparison between SSC, KMS, S3, and SSC 3, or planning to do that as well? Whether regarding CPU usage or
We thought about KMS, but I think the more popular option was the adoption was the S3, so we went with it because the test cases were already around so many. But again, I want Daniel to, as a PM side.
Kyle.
I can't hear it. Can you give him mic?
Yeah, so a little bit what Kyle was mentioning there is that the impact in performance is going to be more or less similar. No, we just tested with S3, but the KMS, at least with the basic round trips going to the key manager, is going to happen. It's true that Adam was mentioning that with S3 it will be a little bit worse with what we tested than with KMS.
It might be.
And then to Kyle's point, that's one thing that Adam is going to work on is all of the round trip, improving all of that. But then there is a lot of improvements that Kyle mentioned then on the algorithm that you're using, if you have in the CPU, the encryption for the algorithm, etc. No? So yeah, all of those things are being worked on.
Okay, thank you.
Thank you, Jiffin.
It's a long walk to the microphone. It's like the walk of honor there.
Yeah, so you had data about the HA proxy ingress. Do you have any data about other ingress methods, especially with Rook, like for Cilium or anything like that?
Yeah, that's a good point. We only tested with HA proxy in the sense that that's what comes out of the box with Ceph ADM, no, when you deploy the ingress. But we didn't do any extra testing with the load balancer. But it's a thing that I'm quite interested on doing, actually, as you said, maybe with what is provided with Kubernetes. But then we could test like with BGP, with Metal LB, different load balancing methods. Is something that I have in my head to try and make a comparison of the different ways in which we could do different load balancing that is not just ingress. But to answer your question here, we only tested what comes out of the box there with Ceph, not with the ingress HA proxy stack.
And we believe that these results are with default config. If we could have thought a little bit of tuning it ahead of the testing this, we would have gone a very better result. But I think, as I think in single node performance, as a developer, they tested it, this already configured. We just want to repeat that we didn't get time. So I think they will not be that bad how they are once we reconfigure the HA proxy with non-default configs, like max number of connections and these kind of things.
No, that's the thing, that with this testing, we didn't mention it, but like for the config, let's say, or the tuning, we didn't do anything. No? Like out of the box, when you deploy RGW, etc., we didn't change any parameters, so things could improve if you actually get down into the weeds. And that's why maybe with the ingress service, with the HA proxy, you could get better results if we improve the defaults, just by improving those defaults.
Right. Gotcha. Thank you.
Thank you.
Any other question? Thank you, everyone. I hope you have rest of your day. Good day.
Thank you.
Thank you for.